Okay, so last time Hannah shared something. Okay, homework for next class. Find one more example on group action and include reference. Okay. Can somebody share? Group action. Vian, do you have something? Oh, let me check if you can share. All right. Do you have it?
No, no problem.
No?
No.
Oh, remember to find one. Nobody remember? Ain, do you get one?
Provide. I will just show you.
Yeah.
Prof, can you share my screen?
I just did just now. Yeah.
Okay. Can you share? Can you see my screen?
Yes.
Okay, this is I got from internet. So this is the definition. I just wrote down. So I got this.
Okay. So what is your action?
The group, the H.
Just the multiplication.
Oh yes. Left multiplication.
Okay. So X is a group H and G the same group. Okay. So Ain has chosen X and G to be the same group H, right? So this is the group action from G cross X to X. EX is X for all X in X. Right, so if let X equals G equals H, a group, right? So for a group, of course, E, the element in G, right, which is now the identity, you multiply that by X, X also in H, right? And this is definitely equal to X, right? So this is the easiest one. Okay, you have EG also in EG. This one is actually the, oh, sorry. This is actually the identity of G, which is in G, which is H in our case. Okay, so they are equal. Okay. The second one is G1, G2, star X. They are all element of. They're all element of H. So this, because group is associative, right? Because the group is associative. So, all right. What is that down there? Oh, the dot one is just the multiplication. Okay.
Okay, this is a reference. I got it not from the journal.
Okay, so this is lecture notes that they share, right? Okay, anyone else? Anyone else? Okay, this is like example 213, yeah? More or less. But example 213, H is a subgroup, right? X is H is a subgroup. That you can also do. So you can also do your case just now they are equal, but they can also be a subgroup. Okay, now example 214 is one example that is very, very famous. Conjugation action. Okay. Okay. In my class last time, I introduced conjugation while doing Silo theorem, chapter 10. Okay. And how do you define a conjugation? Okay. All right, we write. How do I write it? Let me. Copy from our note last time to use the same notation. Okay. I use inverse first, yeah. Okay. I use this. G is conjugated. G is conjugated by 50. Some books they put H, G, H inverse, but it's okay as long as you are consistent. Okay, this is the conjugation action. Okay, if you have, you remember conjugacy class? You learned about conjugacy class before. The conjugacy class for an element X in G is you take all element G in G, you multiply G inverse X G, right? So you see what happened if G is a billion. The conjugacy class of X. So if G is a billion, you can do this, right? This is equal to just singleton. Okay, and then we can count the number of conjugacy classes of G. We use KG. How many? Because each element X in G is a singleton. So if you have 10 elements in the group, you will have 10 conjugacy classes. So we use KG as the number of conjugacy classes of a group G equal to the order of the group G. That is for a billion group, right? Okay, this can be also an action because you conjugate E. So if you put Just now, um, okay, G star X is X inverse GX. Conjugation action, right? Okay, so you check EX. The other way around, sorry. What did I put there? Right? G X on X, right? Okay, this is the action. Okay, so this is what? E inverse XE, right? E inverse XE. So X. Right? Then you can check number 2. You just show you need to show G1, G2, star X is G1 star G2 star X. So you start with the left hand side. This is equal to G1, G2. This is the formula. X to the G1, G2, which is equal to G1, G2 inverse X G1, G2. Which is equal to, right, G2 inverse, G1 inverse, X, G2, G1, G2. I continue up here. This is equal to G2 inverse, this one, you see this? This is G2X, right? This is G2X. We want to show, right? Which is, if G2X is G2 inverse X G2. G1, sorry, G1X. Then G2. So this is G2 of this, right? So G2 of G1X. somehow the G1, G2 is back, right? This one, so be G1, G2. So take this one. So X to the G1, G2. So get that G1, G2 inverse X G1, G2. So this is G2 inverse, G1 inverse, X G1, G2. So take this part, that is G1 and the X. Good. You can also write it as and G2 to that one is X G1, G2, right? With G2. Okay. But somehow, okay, so this is G1. I think this part. Okay, anyhow, that is how you you use the action and to check the two properties, right? Okay, we have to move on to, okay, next one is the, let's just define this isotropy subgroup. Okay, let X be a G set. This means Gx on X. Okay, and X in X. So we have that two properties. The subgroup Gx is the isotropy subgroup of X. So okay, what is Gx? All elements G, all elements G such that when you apply G to X, it is X. So that means G does not change the X. Okay, or we say G, X is not moved by G. Okay, X is not moved by G. We have seen this before in permutation group, right? In which, you remember, we have orbit, if you remember, right? And what is another one? Orbit and stabilizer. remember? In which you apply the permutation, it does not change, right? So this is something to do with the isotopy subgroup. Okay. So E is always in here, right? This is subgroup. That's the word. It's subgroup. So it's a subgroup of G because E. Okay. Proof that Gx is a subgroup of G. I give you 2 minutes. Okay, try to prove that the isotropy subgroup, this side is a subgroup. You have to prove 3 things, right? Okay. So first, just want to check if E of G is in Gx. So you multiply E by X. Yes, since E times X is X. Replace G by E because it's an action, right? So by the first one is this. Number 2, if G1, G2 in Gx, then is it closed, right? Is it closed? Identity is option, but we show close and inverse, right? Subgroup test. Okay, so I put this up here. Okay, since G1, G2 in Gx, then G1x is X and G2x is X. Then G1, G2 of X is, by the second property, is G1, G2x, right? Which is G1x, which is X. So G1, G2 is in Gx. That one is the inverse. That one is the inverse. So if G in Gx is the inverse in GX. Yes or no? How do you show that? Okay, so since G in GX, then GX is X, right? Since G is a group, the inverse exists. So try to multiply by G inverse, right? Multiply both sides by G inverse. Okay, so this one by the property is this. And this is E. So this is this. So G inverse X is X. So G inverse is also in GX. Okay. So we conclude that GX is a sub. Okay. Okay, the last part of this chapter is about orbits. Okay, and this is related close to dynamical system. Okay. Now, you have seen orbit, but I will again mention about orbit. If you don't remember, go back to previous semester or what you have learned before about orbit. Okay, I mentioned about orbit in theory 1. We have a set, then you partition into orbit. Then it is also an equivalent relation. Okay, the orbit of X. Okay, let me rewrite in case you don't remember orbit. Orbit is in which chapter? Eh? When we talk about permutation. Eh? Anyone found it? Which page? If you have this, it's page 106. Okay. So this is in chapter 7 when we learn about coset. Okay, we talk about orbit of a point, but this is based on permutation. Okay. So we have let G be a group of permutation. On the set, 1, 2, until n. Okay. for each one less than I less than n, let ig, okay, is the image of I under phi. Image. Okay, so this is the subset, right? So IG is a subset of, let me call this S. Okay, and when we learn about this, we learn about stabilizer. Stabilizer is the one that fixes. In G. Okay, the stabilizer is the one that fixes. So we take all the combination, but IG is the image. You collect the image. And this is what I call it the partition. Okay, the partition of the set. The set S, if you have like 1, 2, 3, 4, you can have like okay, the image, it can be say 1, 2, right? This is 2G. Example 3, 4, something like this. Okay, so the answer is the partition of this set, right? And it's an equivalent division. Okay, now we have a theorem. Just leave that. In this chapter, get this theorem. Let X be a set and G a group. I just put together be a G set, right? Meaning Gx on X. G is a group. And X on X. Then the order of this orbit, isotropy subgroup, I call it. The order of this is this. Last time I used this. It's the same thing. Index, right? It's the index. Okay. So you see that it divides. If G is finite, it divides the order of G. Let's look at one example. Let X be a D-force. Dihedral group of order 8. Okay. We have G1 is 1, 2, 3, 4. What is G1 is 1, 2, 3, 4? Set X. X is 1, 2, 3, 4. let's see, okay, this is the dihedral, right? I want to write dihedral in terms of permutation. Okay, so first one is R0, okay, R0. Then R90 is rotation, right? 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1, right? So this is R0. This is R90. Now I have R180. 1 goes to 3, 3 goes to 1, 2 goes to 4, 4 goes to 2. That's 180, right? And then we have 270. 1 goes to 4, 4 goes to 3, 3 goes to 2, 2 goes to 1. Okay, and then we have horizontal, right? 1 goes to 4, 4 goes to 1, 2 goes to 3, 3 goes to 2. Then we have vertical. 1 to 2, 2 to 1, 3 to 4, 4 to 3. Then diagonal, 2 to 4. Okay, 1 and 3 does not move. And then the other diagonal, 1 and 3. This is a subgroup. I can put isomorphic. Okay, D4 is isomorphic to H, a subgroup of S4, right? This is a subgroup of S4. S4 is order 24. So we want to find a subgroup of order 8, which is isomorphic to D4 in terms of permutation. So this is how I get the subgroup of S4 of order 8 to match D4 by rotation and reflection, yeah? Okay. So now I want to find all the isotropy subgroup. So this is X. There's a typo, yeah? X is 1, 2, 3, 4. Okay. This X on this. Okay. Now I want you to list all GX. So list G1, G2, G3, G4. Okay, and remember, Gx is G in G, Gx is X. Okay, so this is your part of your D4. So you have to find this, that, when you apply to X is equal to X. Okay, for example, 1, right? Because you apply 1 to here, it's still 1. Okay, this one, no. Because you see a 1, you apply 1, it goes to 2, right? So 1, this one is actually, G is from 1 to 1. G is from 2 to 2, 3 to 3, 4 to this. Okay? And when you apply this to 1, G is from 1 to 1. So you get the same thing. Okay? For this one, it's actually, right? So when you apply 1, it's 2. Right? So when you want to write, G1 is 2. It's not 1. But it's confusing because if I put like this, you think this is a permutation. It's G of 1. It's a mapping. Okay, this is how you write. Okay, so what else? Nothing, right? Just that, right? Oh, here. You see? This one, there is a 1, there's a 1, there's a 1, there's a 1, there's a 1, right? Just okay, which is 2, 4, which is D. That's why I get that D in the notes, right? D. You see? Okay. Okay. What is, so you see 1 is all in here, right? Because whatever you apply to 1, it is still there, right? So 1 is all in here. Now you look 1 with no 2 inside. This one, right? Okay, 1, 3. 1 goes to 3, so 2 stays. 2 stays, 4 stays. The same thing with 3, right? And the same thing with 4. Okay. All right. So that's it about the orbit isotropy. So this is actually the review. We have seen this in permutation, but try to apply this for group action. Okay. In this case, group action is like permutation. I can change to like conjugation, and then you can find some other isotropy subgroups. So it depends. Okay. I hope you will try to find other examples. Okay. When you go back, try to find other examples of isotropy subgroups. Okay. Orbits normally we match to permutation, but try to find one with like conjugation action. If you have not found like what I showed just now, that is the regular multiplication of groups. The other one that I show is on conjugation, but there are many other action. Okay, you try to see besides conjugation, we have some others. Okay. Okay, let me move on to, let's see. Okay. Last time I gave you exercise 1, right? I haven't gave you exercise 2. Not yet? Hannah? Not yet. Okay. But I've done all this actually. But I need to give you marks, right? Let me see. I think you can do all 5 easily. The group of order 8, just a matter of write it out properly. Okay. Find subnormal series which are not normal. We've done this, but write up. And all normal series, remember we draw the subgroup lattice of the group. Okay, you draw that and you see all the series. Which one is a refinement to other one? You remember, one is the shorter one is a longer one, right? Just as a review, this will be also a very good review for test later. Okay, and find an upper central series. We did this also. Just write up so I can give you a proper marks. Yeah. Okay, then you repeat with quaternion. Okay, so you remember quaternion, we also have the subgroup lattice. If you want to draw subgroup lattice, also okay, just to have a proper documentation. But we have not really done number 3, which is good if you can draw. It's a little bit big. Okay, symmetric group of order 24. Okay, you can actually refer Google and see and compare everywhere you can find, because S4 has 5, right? Subgroups of order 8. Last time, I think we did that last semester. The subgroup lattice is quite big. So number 3, there are so many. So don't submit number 3. That will be hard to grade. But for you, as a good exercise, because number 3, a symmetric group of order 24. If I want you to write all subnormal series and all normal series, that will be quite a lot. Okay, but it's a good exercise. Just no need to submit. If you have question, then you can do it. Okay, so 1, 2, 4, and 5, right? Hannah, you will help me to remind later in the group, yeah? To be submitted, to be handed in next Wednesday, next week. Exercise 2, number 1, 2, 4, 5. And then number 3, just to do for own record. Okay? Okay, any question? Right.